Next on our list is solving rational equations. And this will require an LCD as well, but we'll use it a little bit differently than we did when we were adding and subtracting. So let's start by finding out what that LCD is. We have an x plus 4 and an x plus 2. Those are not factorable, so we can just say, well, we have to have the x plus 4. Whatever the first fraction's denominator is, you just write it down. And then you move on to the second fraction. And if the factor is already on your list, you skip it. But if there's a factor that's not on your list, you add it. And when you have something that's not factorable, what we're thinking is that this is an x plus 4 times 1, and this is an x plus 2 times 1. So the entire x plus 2 is a factor. You can't look at the x and the 4 or the x and the 2 as separate. When we go to the right-hand side, we will need to factor that. So I will split the x squared up into x times x, and then I need factors of positive 8 that add up to positive 6, so that will be a 2 and a 4. And when I look at my list, I already have both of those, so I don't have to add anything to my LCD list. So here's what's new. Instead of trying to build all of the fractions up to have the same denominator, when you're solving an equation, your goal is to get rid of the fractions completely. So we will multiply both sides by that common denominator. So there's the right-hand side multiplied by x plus 4 and x plus 2. And the left-hand side will also be multiplied by x plus 4 and x plus 2. And this looks a little funny on the left, but if it helps you line things up, you can write that over 1. It's basically going to multiply into the top of all of these fractions. So I'm actually going to write this out fully just so that you can see what happens. But it's okay to shorten this up just a little bit. There's a step you could skip here, I think. Okay, so we multiply the first fraction top only by x plus 4, x plus 2. So note that you're going to have to be really thoughtful about when you're doing top and bottom versus top only. Second fraction multiplied by x plus 4, x plus 2. So that's 1 times all of that, all over x plus 2. And right-hand side, 8 times x plus 4, x plus 2, over x plus 4, x plus 2. Okay, so again, you don't have to write this out. If you start to be able to see how things will cancel, that's great. But if in doubt, do the extra writing. I know it's a little bit of a pain, but it'll help make sure you don't make mistakes. In this first fraction, I get to cancel an x plus 4. So I'm left with an x and an x plus 2. In the next fraction, I can cancel the x plus 2, so I'm left only with the x plus 4. Those parentheses are really important. We need to subtract the entire thing, so just be careful about that. With subtraction, it's always a little bit tricky. Keep parentheses. On the right-hand side, I actually get to cancel both of those factors, so all that's left over there is an 8. I'm liking that. So we have successfully turned this rational equation into a quadratic equation, and that's always our goal, change from a rational equation into hopefully a quadratic or linear equation, but it should at least turn into some sort of polynomial equation. I am going to clean it up a little by distributing. I have an x squared plus 2x and then a minus x minus 4. Now I'm seeing the quadratic even more. To solve a quadratic, if there's only one x, you can use inverse operations, but here I have x squareds and x's, so I'm going to set it equal to 0 and hopefully factor. If not, we can quadratic formula. So I see an x squared, and then I have a 2x minus x, so plus x, and then I'm subtracting 8 from both sides, so there's a little minus 8 happening here, which means I really have a minus 12. And that does look factorable. I like it. So I split up the x squared into an x and an x. And then I need factors of negative 12 that add up to 1. So I think I want a 4 and a 3. And I want it to be a positive 4 and negative 3 so that I get that 3x and 4x, and the 3 is negative, so it adds up to positive 1. Okay. This is telling me that x is either going to equal negative 4 or positive 3. You need to be really careful anytime you have an equation that involves functions with domain problems. The solving steps also involve the possibility of introducing extraneous solutions, which means you end up with an answer that wasn't actually valid for the original equation. These are fairly easy to spot. For rational functions, you just have to remember to do it, and you can either remember at the beginning or the end. I do this at the end, but if it helps, you can do it at the beginning as well. What we're checking for is basically just that the denominators don't equal 0. So if x equals -4, we get -4 over 0 as the very first, this fraction right here. So this is not okay. If we check the x equals 3, we get 3 over 7, and that was a minus 1 over 3 plus 2, 5, equals 8 over, and then whatever that mess is, I guess it's 7 times 5, 35. And you can actually do a full check. You can plug that into a calculator. That's not a bad idea. But what we're really looking for there is just that none of the denominators are 0, and they're not. So that one does not look like an extraneous solution. So absolutely a full check just to make sure you didn't mess up is good. But this non-optional check is, it doesn't matter how confident you are, you need to make sure you don't have an extraneous solution in there. You can do all your work correctly and get a bad solution.